Hi, welcome back to a new video from Reading Research Papers series. Today, I'll be introducing you to a very interesting paper. It's actually a small paper. It's called VisualBERT. The title of the paper is VisualBERT, a simple and performant baseline for vision and language. So from the title itself, you can know that it's a vision language model. BERT was a language model. So VisualBERT obviously has got something to do with vision. I came across this paper. It came out from I would say, I think looking at the researchers, it was a collaboration between UCLA and Peking University in China and Allen Institute for Artificial Intelligence. So it's a very nicely written paper, and the number of citations actually is not that high compared to rest of the papers in this domain. It has around 2,500 citations. So there were a set of two papers that I came across. One was called VisualBERT, and the second one is VisualBERT. And then I realized that, okay, maybe going through VisualBERT first will be a very good idea. Plus, it's also going to be a very nice transition because in one of the earlier lectures in this series, we had gone through the BERT paper. So it'll be nice to know how you can utilize BERT in a vision language model. So I came across this paper while diving deep into VLMs, vision language models. And I'm, of course, as you might have figured out from my BERT video, I'm very fascinated about the BERT model. So I was also equally fascinated just to see how people implemented BERT in the context of VLM. So this paper is actually very nice paper. I love the way it is written. It's very easy to understand relatively. In the one of the last lectures, we were dissecting Swin transformer paper, and I was constantly saying the writing is very difficult, Swin transformer, the way it is written. But that's not the case with VisualBERT. Also, the figures in this paper, some of the figures are like very, very beautiful, meaningful, and figures that teach you something. I mean, I'm having a black and white print here, so you really cannot appreciate the beauty of this figure, but I'll show you while dissecting the paper. So overall, this paper will give you an idea that, give you an idea about how to combine like a model that can take care of vision and a model that can take care of text like BERT into producing, a unified embedding, like text embedding and vision embedding that are pretty much aligned with each other. When I read the paper for the first time, I felt like, oh, wow, if I knew all these things back then. So this paper was published in 2019. I honestly felt like, oh, if I knew all these things meaning all the things about the models like BERT and other computer vision models, maybe I could have also proposed a model like this. But I mean, it's very naive of me to think like that because anything is easy in retrospect. I'm sure this was the result of hard work of multiple years of hard work of all these people who are authors on the paper on this research. So no disrespect, but I still felt like, oh wow, such a simple, elegant idea, and why did I not think of this before? So that is why I'm so fascinated about this paper. So I will try to, do this dissection in one sitting. I'm sitting at around 2 p.m. on a Thursday afternoon. So, of course, it's very different from how we did Swin paper. I was trying to do it in the morning, but, we should be able to put our brain to focus at pretty much any time of the day if it's during the working hours. So I'll attempt this. If I feel so tired or something in the middle, I'll simply take a break and I'll continue the recording afterwards. But I'm hoping that I can finish it in one sitting. That being said, there are totally 14 pages in the paper, out of which last 5 pages are references plus big figures. So the core content, the textual content of the paper is in the first 9 pages. So just to give you an idea, like how big the paper is. Some papers like clip paper, it's like 48 pages. It's like huge. One reason why I so badly want to do a review of clip paper in this series, but the only reason that is preventing me from doing so is the huge number of pages. I have read it myself, but dissecting is very different from reading it passively and doing it yourself, right? So, but I'm happy that VisualBERT is going to be hopefully a relatively easy journey that you're going to enjoy now. So now let's get into the paper. So this is the VisualBERT paper. I have not made my own annotations yet, but I will make it as I go through the paper. I recommend you to print it if you have the ability to print, and go through the paper by putting your hands with a pen or pencil on the page itself, and going through it line by line as you listen to this lecture video. But if not, you can simply open a PDF document or something on the side, and so that you're also going through the paper on your own while listening to me. So this is the VisualBERT paper, around 2,500 citations, and there are a lot of similarities between VisualBERT and this paper, which I'm going to do a dissection sometime in the near future, called VisualBERT, which has around 5,000 citations. So this paper came out from a group of researchers affiliated with Peking University, Allen Institute, UCLA. Let's actually get into the paper abstract itself. So VisualBERT, a simple and performant baseline for vision and language. So it's basically a VLM, vision language model. Abstract. We propose VisualBERT, a simple and flexible framework for modeling a broad range of vision and language tasks. VisualBERT consists of a stack of transformer layers that implicitly align elements of the input text and regions in an associated image with self-attention. So basically, if we have a sentence describing something, and if we have an image which carries some part of the sentence description, then the words that are in the sentence which are describing some specific pixels in the image, you can create very high degree of association with them, and that too with the help of self-attention. We'll see how this is done, but basically you can imagine somehow you are passing tokenized text and tokenized image into transformer somehow, right? We'll see how the paper actually does that. But this alignment is one of the key issues or key challenges that researchers are trying to solve. If you look at the text which says apple, and if you look at an image of an apple, they both should mean the same thing. So if you're converting the text of an apple into a vector and an image of an apple into a vector, then those two vectors should have high degree of cosine similarity, ideally, assuming they are in the same space, in the same representational space. We further propose two visually grounded language model objectives for pre-training VisualBERT on image caption data. So image caption data, we know it's like it's collected. One way in which it is collected for clip paper is by taking image and their alt tags from websites. But image caption data will be image caption data pairs, and like that 400 million or something like that pairs were used in clip paper. Here we'll see how many are being used. Experiments on 4 vision and language tasks, including VQA, VCR, NVLR2, and Flickr 30, show that VisualBERT outperforms or rivals the state-of-the-art models while being significantly simpler. So now the question is, what is VQA, VCR, NLVR, Flickr 30, etc.? VQA is visual question answering. VCR is visual common sense reasoning. And let's look at the details of NLVR and Flickr 30. So what I'm going to do is I'll take a screenshot and I will ask ChatGPT, which we always do. So in this series, we have no shame in asking ChatGPT what is the answer for something. So let me ask, what is NLVR? I think it's natural language visual reasoning or something. And Flickr 30 dataset. 30 or 30K? I guess 30K. I'm sure it's maybe 30K image caption pairs. I'm not sure. Let's see. So NLVR is, yes, natural language visual reasoning, synthetic images, and NLVR2 uses real images. So NLVR was using synthetic, and now we have real images. NLVR2 consists of pair of images, natural language statement, and a label. Then the model must decide, is this statement true about the pair of images? The left image contains exactly 2 dogs and the right image contains none. Okay. Then image A has 2 dogs, image B has 0 dogs. If the model is seeing something like this, the label, ground truth label, will be true. Otherwise, ground truth label will be false. So basically answering, like having a label, which is a statement about the pair of images, and the statement can be true or false. Then visual reasoning / grounding. It tests whether a model can count the objects, it can compare the 2 images, understand spatial relations, match text to visual scenes, reason, not just classify. Okay. So that is NLVR2. Now Flickr 30 dataset is what? It's a large image text dataset containing around 31K real world images and 5 human written captions per image. So each image should have 5 captions. So around 150K captions, 30 multiplied by 5. What is it used for? It can be used for image caption generation, then caption to find the matching image. So it's like retrieval. So you try to retrieve the best matching image corresponding to a caption. Then phrase grounding. So every noun phrase in the caption, a woman, a red jacket, is linked to a bounding box. Okay. This also we'll see. So the bounding box hopefully should contain a red jacket or a woman, whatever is being described in the text. Okay, so these are the data sets. And then visual question answering and visual common sense reasoning, we'll see what those data sets look like. Further analysis demonstrates that VisualBERT can ground elements of language to image regions without any explicit supervision. So this grounding or alignment is something that we are trying to achieve, right? You want to ground what vision model is seeing and what the language model is understanding. And hopefully we should be able to do this without any human supervision. So when they say explicit supervision, it simply means there are no humans sitting down to annotate the images to do this. And is even sensitive to syntactic relationships, tracking, for example, association between verbs and image regions corresponding to their arguments. So let's see all of this. Let's see how images and captions are aligning, how visual question answering, visual common sense reasoning, etc. is accomplished using VisualBERT, and how is VisualBERT significantly simpler compared to the state of the art at that time. Please remember, this paper was released in 2019. So obviously there are better models now, but we want to know how models evolved, right? So you have to have a deep dive into simpler models to truly appreciate the evolution of the field. So that's what we are trying to do here. Now let's move on to introduction. Tasks combining vision and natural language serve as a rich testbed for evaluating reasoning capabilities of visually informed systems. Beyond simply recognizing what objects are present, so this is simply classification or object detection. Beyond that, vision and language tasks such as captioning or VQA, visual question answering, and visual reasoning challenge systems to understand a wide range of detailed semantics of an image, including objects, attributes, parts, spatial relationships, actions, and intentions, and how all these concepts are referred to and grounded in natural language. So basically, if we are just trying to do object detection, let's say detection of an object of like an object means it can be human or dog or actual object, whatever. The dog could be running, dog could be sleeping, but dog is just detected as dog through a bounding rectangle. It has no other information or it has no other capability for extracting more information. But here, if it's a, let's say, image caption pair, maybe the caption of an image where a dog is sleeping versus a caption of an image where a dog is running, it's different. And through that image caption pair, when you are training a vision language model, by grounding the visuals in natural language, meaning by describing the image through textual captions, and by training a model to learn from both, you can learn a wide range of details in the image, like objects, of course, but attributes of the objects. Let's say it's a jacket. What's the color of the jacket? Or different parts, or spatial relationship. The dog is standing on top of a building, something like that. Or actions like sleeping, running, or intention. So a lot more details you can extract from visuals that are grounded in natural language. In this paper, we propose VisualBERT, a simple and flexible model designed for capturing rich semantics in the image and the associated text. VisualBERT integrates BERT, Devlin et al. So BERT paper, obviously one of the most famous papers in the history of AI, a recent transformer-based model for natural language processing. So this is the attention is all you need paper, and this is the BERT paper. And pre-trained object proposal systems such as faster RCNN. So RCNN, fast RCNN, faster RCNN, mask RCNN, they were all either object detection or semantic segmentation models. And it can be applied to a variety of vision language tasks. So basically, this paper shows that BERT which was originally used for natural language processing, and models like faster RCNN, you can combine to build one single model, which can be used for tasks that involve both vision and language. So obviously you can see that the part where the model that takes care of language will be BERT, the model that takes care of vision will be faster RCNN. In particular, image features extracted from object proposals are treated as an unordered input tokens and fed into VisualBERT along with the text. So you can use faster RCNN or similar models to extract something called as object proposals. Object proposals are smaller bounding rectangles, which are not as big as the image itself. And those bounding rectangles may enclose different objects in an image. So those are called proposal regions. And those proposed regions can be passed along with the text that describes the image into VisualBERT. The text and image inputs are jointly processed by multiple transformer layers in VisualBERT. So obviously, I mean, VisualBERT will have BERT, which means there will be transformer layers. And here they are saying there are multiple transformer layers in VisualBERT. See figure 2. Where is figure 2? So this is figure 2. So in figure 2, a person hits a ball with a tennis racket. So this is the image and this is the caption. So this is the image caption pair. And what is done is the image is, it seems to be, you are extracting different region proposals using faster RCNN. And those regions are now passed as separate tokens. So you have one all the way till k. So you have total k tokens corresponding to k image proposals from faster RCNN. And I'm sure in that token, you first create token embedding. You add a token corresponds to segment. So this is segment A, and the next one is segment B. In BERT paper, we were having two segments. If we wanted to, let's say, classify whether sentence B is following sentence A or not. So there was a separator token. So this separator token will separate between the two sentences. There was CLS token at the start, and then there were two sentences, sentence A before the separation and sentence B at the end. And at the end also there may or may not be a separator token. So here also it's more or less the same, except it's not two sentences, it's one sentence and an image. So everything here corresponds to the sentence. Now I'll come to why do we have this mask token, but this is the sentence which describes the image. A person hits a ball with a tennis racket. Then these are the tokens corresponding to the different region proposals that faster RCNN gives you. So you pass them as tokens. So now you have a sequence of tokens separated by a separator token and prepended by a CLS token. Inside the text token, some tokens may be masked. We'll come to that. And then these tokens that are converted into embeddings, then segment token is added, which says whether it's from image segment or text segment. Then position embedding is added. And after all of this is passed into a sequence of transformer blocks. And then transformer block will convert these tokens into context vectors. And using those context vectors, we can do different tasks, right? So figure 2 caption is the architecture of VisualBERT. Image regions and language are combined with a transformer to allow the self-attention to discover implicit alignments between language and vision. So now the transformer can create attention scores, where attention score might be between this textual token and this image token, right? You can have attention between some random text token and random image token. You will have attention between text token and text token because it's self-attention. So whatever tokens are coming, irrespective of whether it came from image or whether it came from text, you are constructing attention between the different tokens, irrespective of what the origin of that token was. It is pre-trained with a masked language modeling objective. So this MLM or masked language modeling objective was one of the objectives of BERT also. So masked language modeling is, if you have a sentence, some words you will mask, and then you will try to predict what is that mask token. So this is the final classification token corresponding to mask, and your objective 1 is to predict what this masked word is. You know the masked word is probably racket because that is the last word. And if we say that each token is a word, for simplicity, of course, each token is not a word. Each token can be a word or subword or character. But if we assume that each token is a word, in this example, the context vector corresponding to this mask token should ideally be predicting that the mask is racket. So that is the objective one mentioned here. So objective one. And then second is sentence image prediction task, objective two, on caption data, and then fine tune for different tasks. So objective two is accomplished using the classification, using the context vector of which token, using the context vector of classification token. So look at this. Objective two is accomplished using this token, this context vector. This context vector is resulting from the CLS token, classification token. Now, let's say my goal is to say whether this and this are the correct image caption pairs or the wrong image caption pairs. Then maybe my CLS token should predict 1 if they are correct image text pairs. If they are not correct image caption pairs, it should predict 0. So you can use this CLS tokens context vector for accomplishing objective 2, which is saying whether the image and the caption are related to each other or not. And you can use the mask tokens, which was originally part of the masked language modeling in BERT. Actually, let me show you the BERT paper in case you don't remember. So it has almost 150,000 citations. It's like a very, very, probably one of the most famous papers in the history of AI. But see, this was one of the, this was the BERT model architecture, but there is CLS token. Then CLS token is used to predict next sentence. NSP is next sentence prediction, saying whether the first set of sequences which are corresponding to sentence A, followed by a separator token, then followed by another set of tokens corresponding to sentence B, whether the sentence A and sentence B are sequentially followed, like whether sentence B follows sentence A sequentially or not. That is what the class token, CLS token, does. The mask token simply tries to predict what the masked word is. So it's called MLM or mask LM for masked language model. So these are the two objectives. Okay, so I hope you understand briefly how the model works. The rich interaction among words and object proposals allows the model to capture the intricate associations between image, text, and image. What do we mean by rich interaction among the words and object proposals? Object proposals are the tokens corresponding to image. The words are sort of tokenized sentence, and the interaction between those two are captured through what? Captured through self-attention. So the transformer self-attention will create attention scores between different tokens. So that is how you capture the relationship between words and regions in an image. Similar to BERT, pre-training VisualBERT on external resource can benefit downstream applications. In order to learn associations between image and text, we consider pre-training VisualBERT on image caption data, where detailed semantics of an image are expressed in natural language. So see, this is the difference between classification and image captioning. In classification, whether you have an image of a dog that is playing or running or sleeping or whatever, jumping, all of that is classified as dog. And whether you have different types of images of cat, it's all classified as cat. So then it becomes a binary classification. So you are not forcing the model to learn anything special. It's just learning basic classification. But then in captioning, the caption will be different for all the images. For every unique image, you will have a unique caption, which means the model is forced to learn a lot more things. That's the power of, image caption dataset. So through image caption data, detailed semantics of an image are represented in natural language. Where in natural language? In the caption itself. We propose two visually grounded language model objectives for pre-training. Objective number 1, part of the text is masked. We saw that. And the model learns to predict the masked word based on the remaining text and visual context. So basically, you have the full visual context available in the form of region proposals. Using the visual context and using the unmasked words, you try to predict what is the masked word. So this is the objective number 1, MLM, masked language modeling. Objective number 2 is the model is trained to determine whether the provided text matches the image. So what if I provided a wrong image caption pairs? Then my model should say, hey, this is not the correct image caption pair. The matching between these two this pair is very, poor. So the model should be able to say that. So we show that such pre-training on image caption data is important for VisualBERT to learn transferable visual text and visual representation. So the end goal is not just to do image captioning or image caption recognition. The end goal is to make this model trainable for other downstream tasks, maybe like visual question answering or common sense reasoning, etc. But for that, to make the model kind of equipped for that, what should we pre-train it on? We may pre-train it on image caption data. So that is what this paragraph is saying. We conduct comprehensive experiments on 4 vision language tasks: visual question answering, VQA, visual common sense reasoning, VCR, then natural language for vision reasoning, NLVR2. So these are those naturally occurring images. We saw the data set. And region to phrase grounding, flicker 30. So basically, different regions in an image, there will be bounding rectangles and there will be phrases which correspond to what is present inside that bounding rectangle. We'll see the details when we come to the experimental section. Results demonstrate that by pre-training VisualBERT on COCO image caption dataset, VisualBERT outperforms or rivals the state-of-the-art model. Amazing, right? We are yet to see the full architecture. I mean, we saw it in figure 2, how it works, but I hope they will show the architecture somewhere. We'll see. We further provide detailed ablation study to justify our design choices. Further quantitative and qualitative studies analysis reveals how VisualBERT allocates attention weights to align words and image regions internally. So this is a very important thing. In fact, you might have seen when I scrolled down this figure 1. This figure 1 is definitely a very interesting figure. I want to walk you through this figure 1 because it's probably one of the most interesting figures in this paper. We demonstrate that through pre-training, VisualBERT learns to ground entities and encode certain dependency relationships between words and image regions, which attributes to improving the model's understanding on the detailed semantics of an image. So these 2 sentences might appear a bit confusing because it's a long sentence. There are a lot of complex relationships, but when we go through figure 1, you will understand what this means. So let's now look at figure 1 in detail. Figure 2 we already looked at. So first, look at the left-hand side image. It has bunch of bounding rectangles bounding different things. So this blue bounding rectangle is bounding his white shirt. This red-ish bounding rectangle is bounding this person, the main guy in the image. These pale red or light red bounding rectangles are bounding other pedestrians walking. Then I don't know what this yellow bounding rectangle is bounding. It's bounding, I think I would say these 3 people. I don't know what it is bounding, but whatever, we'll see. So this is the region proposals from the faster RCNN. We can imagine like that. Now the caption is man wearing white shirt is walking on sidewalk alongside other pedestrians. So you just read these words from top to bottom. These words, man wearing white shirt, like that. Okay. So that is the corresponding caption to this image. Now, what is shown here is different layers, layer 1, layer 3, layer 5, 6, 10, 11. So different transformer layers from the VisualBERT model, where they are showing the correlation between a given word and a given bounding rectangle. So where is the given word? This, let me just zoom in somehow. So these are the words: man wearing white shirt, so on. So each row, so what does this entire row represent? This entire row represents the word man. Okay. This is for layer 3, this is for layer 4, layers 5, and so on. Similarly, this entire column represents a red color bounding rectangle. Red color bounding rectangle is this bounding rectangle. And what is that bounding rectangle's label? Its label is man. Now, what we want to see is, ideally, the correlation between the word man and the red color bounding rectangle should be highest. Is there any doubt about that? The word man in the sentence should be highest correlated with, and what is the sentence? Sentence is the caption of the image. The word man in this image should have highest correlation with this red color bounding rectangle. Now look at layer 3. In layer 3, man word, does it have highest correlation with this red color box or this is a light red box. So actually light red box has a brighter color. So this color bar values are given here. So darker the color, lower the correlation, brighter the color, higher the correlation. So obviously for layer number 3, this correlation between man and this light red is the highest. What is light red? Light red is pedestrians. So in layer number 3, the VisualBERT model thinks that whatever is bounded inside this bounding rectangle is a pedestrian, which is true. It is a pedestrian, but ideally the man that we are referring to here is actually there in that. So ideally the correlation between, in the layer 3, the correlation between this red color rectangle and the word man should have been highest. So the value of this should have been the brightest. But now let's move from layer 3 all the way to layer 11. Look at that in layer 11. Where is the highest correlation? The first row is man, and the first column is this red color box, which is what? Which is the bounding box with the label man. And you can see that here, that rectangle, that cell has the highest value, which means the word man in the caption and the bounding rectangle, which is in the red color shown here, they are highest correlated, and they should be highly correlated because they are mentioning the same thing. So this is how language and vision grounding happens in VisualBERT model. And now look at another one. Look at the word white. This white word was correlated in layer number 3 with the red color rectangle, with the blue color rectangle, as well as the light red rectangle. So red color rectangle is man, sure. Blue color rectangle is what? It's actually white. This blue color rectangle is enclosing that his white shirt. And what is the light red rectangle? It's other pedestrians. So actually the word white in the caption need not be correlated with these light red rectangles. It's not needed because it's not true. But white should be ideally highest correlated with this rectangle. White can also be correlated with this rectangle, perhaps. Sure, because the white shirt is being enclosed in this rectangle also. And if you look at the final layer, so by the time the model is learning, the initial layer, the representation between image and text are not highly correlated. But in later layers, the model is fixing its own mistake. So in the later layer, look at, so white is this row. This row is white. White and red color bounding rectangle are highest correlated. Red color is man. So white and man are highly correlated. White and blue, which is this one, and blue is having a label called shirt. They are highly correlated. The label of this white color, this blue color rectangle is shirt from the faster RCNN. So don't get confused by these names. These are the labels of the bounding rectangles. It is not the caption. This is the caption. These are the words that are part of the image caption. So this caption describes image as a whole. These labels describe what is there inside each of these bounding rectangles. So who is giving you the label and the bounding rectangle? Faster RCNN. Who is giving you the caption? Caption is part of the data, so it's part of ground truth. Now, who's giving you this this kind of correlation map? It is from VisualBERT. The correlation between a given word in the caption and a bounding rectangle is being plotted as like a visual image. That is what is happening in this. Okay, now let's read the caption. Figure 1. Attention weights of some selected heads in VisualBERT. In high layers, example 10th and 11th layer, VisualBERT is capable of implicitly grounding visual concepts. So we can see that in layer number 11, the correlation between words in the caption and the bounding box, it's better. Example, other pedestrians and man wearing white shirt. The model also captures certain syntactic dependency relations. Example, walking is aligned to man in the 6th layer. The model also refines its understanding over the layers, incorrectly aligning man and shirt in the 3rd layer, but correcting them in the higher layer. Let's see where is man and shirt incorrectly being aligned. Let me first delete all of this so that I can easily annotate. So in the 3rd layer, this sentence says in the 3rd layer, incorrectly aligning man and shirt. Let's see. So this is the 3rd layer. man and shirt is being incorrectly aligned, where I don't think in third layer incorrectly aligning man and shirt is happening. Oh, I see. I think it's probably, yeah, I'm not sure if in the third layer man and shirt are being aligned. I'm not 100% sure if this last sentence of the title is correct. But I can see the model making some mistakes. See, the biggest mistake that the model has made is in layer number 3, shirt and pedestrians are highly aligned. See, this light red color is pedestrians. So shirt and pedestrians are very highly aligned in layer number 3. But when you go to layer number 11, that correlation between shirt and pedestrians is almost zero, as it should be. I mean, pedestrians, none of the, I mean, yes, there is one pedestrian wearing a shirt. There's this small guy in the background, but shirt should not be correlated with pedestrians. Shirt is ideally should be ideally correlated with this, or if there was a bounding rectangle here, with that, something like that. Even that is not shirt. Technically, only this is shirt. So ideally, shirt from the caption should not be aligned with the bounding rectangle corresponding to pedestrians. But that is happening in layer 3. But then the model is correcting that its own mistake by layer 11. That is what the figure 1 is saying. I recommend you to spend some time going through all the different examples, like going through this whole right hand side of the figure a little bit, by taking a little bit of time, and then you will understand this whole thing. It's really beautiful. I can pick any number of examples excuse me, from this image caption, or the caption image region correlation, and I can tell you a lot of stories, but none of that will be as helpful as you yourself going through the right hand side of this figure once. All right, so that is figure 1. So now let's move on to section 2. So now everything in this part will make sense when you read once. It's basically saying that the grounding is happening and between vision and text, and that representation itself changes from layer to layer. Okay, now let's move on to section 2, related work. There is a long research history of bridging vision and language. Various tasks such as visual question answering, which is VQA, textual grounding, and visual reasoning have been proposed, and various models have been developed to solve them. So I'm reading by skipping this, okay? So don't think that I'm just, while reading the full sentence, I'm just skipping the these items. These approaches often consist of a text encoder, an image feature extractor, and a multi-model fusion module. So text encoder will encode textual tokens into vectors. Image feature extractor will extract features from the image using CNN or whatever, and then convert it into vector. And the fusion module basically will produce self-attention between all the tokens. And then an answer classifier. Most models are designed for specific tasks, while VisualBERT is general and can be VisualBERT is general and can be easily adapted to new tasks or be incorporated into other task-specific models. Understanding detailed semantics depicted in an image is critical for visual understanding, and prior studies show that modeling such semantics can benefit visual and language models. I don't know. I mean, it looks like there is some sort of spelling mistake here. Visual and language model. For instance, attribute annotations in visual genome are used to enhance the object detector in VQA systems. Now, I'm not familiar with the visual genome. I just want to ask ChatGPT, what does visual genome refer to in this context? What does visual genome, or what is visual genome here? Visual genome dataset used to teach fine-grained visual understanding. Visual genome is a massive dataset of images annotated with objects, attribute, relationships, regions, caption, and question-answer pairs used to build models that deeply understand images at a granular level. So it's not just image caption pairs or image label pairs. It has attributes within the image, and I'm sure there is these graph structures that ChatGPT is showing. It's like showing relationship between different items in an image. Okay. So visual genome is basically a very comprehensive data set. For instance, attribute annotations in visual genome are used to enhance object detector in visual question answering systems. Explore using, or Santoro et al. Explore using an attention module to implicitly model the relationship between objects in the image. Implicitly model using attention, which means I guess there is no hand annotations available to learn the relationships. I guess that's what this implicitly mean in this context. Let me ask. Also, what does the word implicitly mean in this paragraph? Something not say. Yeah, I know the English meaning. I just want to know in this context, what does it mean? No, I don't want analogies or anything. Santoro et al. Explore using attention module to implicitly, using attention module to implicitly model the relations, etc., etc. This is the sentence I am referring to. Model is not directly taught the relationships, okay, but attention mechanism automatically learns the relationships. So does it mean that there is no label data that? So does it mean that there is no labeled data like visual genome that explicitly explains the attributes? I guess that's what, yes, you have understood the distinction correctly. So implicitly means there is no labeled attribute, unlike visual genome. Okay. Lee et al. Takes a further step and explicitly build a graph to encode object relations. In VisualBERT, the self-attention mechanism allows the model to capture implicit relationship between objects. Furthermore, we argue that pre-training on image caption data is an effective way to teach the model how to capture such relations. What do you mean by such relation? The relations that are there in an image. The kid is playing with the dog. How do we know this? Humans know this, but a model will simply see, if it's a bounding, like an object detection model, it will see a ball, it will see a kid, it will see if there is a dog in the image, just that. It will not know the relationship between the different objects. That has to be explicitly mentioned, like in the visual genome data. But here, with visual captioning data or image caption data pair, you can pre-train the VisualBERT model to learn all those things. Our work is inspired by BERT, of course, a transformer-based representation model for natural language. It falls into a line of works that, so here Radford et al. Is, I think it's the OpenAI's paper, if I'm not wrong. Radford et al. 2018, I guess. Yeah, it is the GPT paper from, I guess, OpenAI only. Yeah, this paper also, obviously. So this was the Radford paper, Alec Radford, and then last author you might know, Ilya Sutskever. I really want to do a review of this paper also once. But anyways, let's come back to the paper. That learn a universal language encoder by pre-training with language modeling objective words, that is predicting words that are masked out from the input based on the remaining context. So basically in BERT model, we were having the sentence, and then in the sentence, some words were masked, and we want to know what are the masked words. Two concurrent studies in the, however, next word prediction model, you don't have masking, you rather have masking of the attention. So queries are not allowed to pay attention to keys corresponding to tokens that are in the future, right? So there it's masked attention, self-attention is masked. Here, masking is done for the inputs themselves, not for the masking is not done on the self-attention module. It's unmasked self-attention, but the tokens themselves are masked. In GPT-like models, tokens themselves are not masked, but rather attention is masked. Okay, two concurrent studies resemble this paper. VideoBERT, I haven't read this paper actually. I'm curious to know VideoBERT 1700 citations. These are all interesting papers, yeah, just by seeing the paper, I feel like reading it. I'm definitely going to have a look at this paper sometime soon. Then other paper, I'm sure they're going to mention VisualBERT. VideoBERT transforms a video into spoken words paired with a series of images and applies a transformer to learn joint representations. Their model architecture is similar to ours. However, VideoBERT is evaluated on captioning for cooking videos. So caption for cooking videos, while we conduct comprehensive analysis on a variety of vision language tasks. So here, I guess they used a bunch of cooking videos and corresponding captions to create image, frame caption, pairs or something like that. Then concurrently with our work, VisualBERT proposes to learn joint representation of images and text using only BERT-like architecture, but has separate transformers for vision and language that can only attend to each other. So in this VisualBERT paper, I have read this paper actually, they introduce something called co-transformer, co-TRM. So I can actually show you that. VisualBERT. So this is the figure. So here what they do is they construct queries, keys, and values out of images and text separately. But then the queries of image will attend to values and keys in, it will attend to value. The queries in image will attend to keys in text. Queries in text will attend to keys in image. So that's what these two arrows are showing. So, so this is how cross attention is sort of created between the textual stream and the image stream. But they are saying it has a downside. Can only attend to each other, resulting in twice the parameters, because you need one separate transformer for the image stream and one separate for the text stream. That's why twice the number of parameters. They use a slightly different pre-training process. When this they means the VisualBERT paper, they use a slightly different pre-training process on conceptual captions and conduct evaluation on 4 datasets, 2 of which are also considered in our work. So they VisualBERT considers 4 evaluation on 4 datasets, out of which 2 are there in this paper also. Our results are consistent with theirs. Our model outperforms 1 out of 2 intersecting tasks. Outperforms on 1 of 2 intersection tasks. So in one task, VisualBERT dominates. It outperforms. In another task, VisualBERT outperforms. But the methods are not wholly comparable because different visual representation and pre-training source are used. Okay. This seems like a bit, I don't think it's a strong argument. For sure. But yeah, methods are comparable, right? Or to say that methods are not comparable, the reason should not be the fact that pre-training data set is different. Then why not make the pre-training data set the same? So, if objective is to compare, yes, I understand and agree that we cannot compare because the pre-training is different. So direct one-to-one comparison is different. But I'm sure there are still ways to compare the methods that both papers use. But I understand that results we should not expect to be exactly the same simply because pre-training data set is different. Okay. Now let's move on to section 3, a joint representation model for vision and language. In this section, we introduce VisualBERT, a model for learning joint contextualized representation of vision and language. First, we give background on BERT, then summarize the adaptations we made to allow processing images and text jointly. Because in BERT, you only process text. Here, they have figured out a way to make BERT useful for joint processing of images and text, as seen in figure 2, and finally explain our training procedure. Okay, figure 2 we have already gone through. This is the figure 2. So I won't be going through that again. Background. BERT by Devlin et al. Is a transformer with subwords as input and trained using language modeling objective, masked language modeling, and next sentence prediction, NSP, MLN. Those were the 2 objectives. All of the subwords in an input sequence are mapped to a set of embeddings E. Each embedding E is computed as a sum of token embedding. So there are 3 things: token embedding, sequence embedding, and position embedding. Not sequence embedding, segment embedding, whether it's part of segment A or segment B. Segment A will be the sentence number 1, segment B will be the sentence number 2. So the segment embedding says whether the token that you are currently considering belongs to segment A or segment B. Then last is position embedding. This also is fairly common. That the input embeddings E are then passed through a multi-layer transformer that builds up contextualized representation of subwords. BERT is commonly trained with two steps, pre-training and fine-tuning. Pre-training is done using a combination of two language modeling objective, MLM and NSP. Mass language modeling, MLM, where some parts of the input token are randomly replaced with a special mass token. So some tokens are randomly thrown out and mass token replaces that randomly thrown out token. And the model needs to predict the identity of these tokens. So basically, model will try to predict what is the, from the final context vector corresponding to this mass token, model will try to predict what was this mass token. Next sentence prediction is done using what? You saw the image. It is done using classification token. Classification token will try to predict whether the sentence number B, which is the segment B, is actually following segment A or not, or whether they are completely disconnected sentences, where the model is given a sentence pair and trained to classify whether they are two consecutive sentences from a document. Finally, to apply BERT to a particular task, a task-specific input, output layer, and objective are introduced. Of course, this is part of fine-tuning, and the model is fine-tuned on task-specific data, starting from pre-trained parameters. So pre-training is done using two language modeling objective, MLM and NSP. And then once pre-training is done, you change the output layer, input layer, and training objective to make it suitable for further fine-tuning tasks. Okay, now let's come to VisualBERT model. The core of our idea is to reuse self-attention mechanism within the transformer to implicitly align elements of the input text and regions of input image. In addition to all the components of BERT, we introduce a set of visual embeddings F to model an image. So this we saw in figure number 2. Visual embeddings were these embeddings. These are all visual embeddings. Basically, image regions which you get from faster RCNN converted into a sequence of tokens. Each F, small f belonging to capital F, corresponds to a bounding region in the image derived from an object detector. Each embedding in F is computed by summing three embeddings. One is three embeddings are, one is the visual embedding, vector of not the patch, vector of the object detector's output. Second is a segment token. Third is or segment embedding. Third is position embedding. So F0, a visual feature representation of the bounding region F, computed by CNN. Then Fs, a segment embedding indicating that it is an image segment and not a text embedding. Then Fp is a position embedding which is used when alignments between words and bounding regions are provided as part of the input. Which is used when alignments between words and bounding regions are provided as part of the input and set to the sum of the position embeddings corresponding to the aligned words. I don't understand this sentence. Let me ask. This is from VisualBERT paper. Explain. They do not okay, this I know. No, I know all of these things. This is not what I think model is hallucinating. I'm asking about this particular section. Explain this sentence. Okay, for some reason the sentence is not appearing from the image. I'll just try to copy it from here. Okay, I just manually copied the sentence. This is describing how VisualBERT constructs embedding for each visual region before feeding. Embedding indicating it's image embedding opposed to, okay, this we know, basically segment embedding. VisualBERT mixes text tokens and visual region embeddings. So model must know which token comes from text, which tokens come from image. So this I understand. FP, a position embedding. This refers to position embedding, text tokens. Yeah, but image tokens do not have a natural order. This is the thing that I was looking for. See, in textual tokens, there is position embedding, right? Because text appears sequentially, but image tokens do not have a natural order. So VisualBERT uses a special trick only when alignment information is available. So some datasets like Visual Genome provides region bounding boxes, region descriptions, grounding information, etc., where such alignments exist. Region is aligned to words in caption. Example, bounding box number 12 aligns to the words red ball. VisualBERT uses this alignment to give the region a position embedding. I see. So normally, for normal, I would say image caption dataset, we don't have this alignment data as part of the training, which means we won't be able to give any position embedding. So what if alignment data is not there? In that case, what will be the position embedding for images or for image, not patches, image regions? What if my data set is simply image caption data? So if your dataset is just image plus caption and you do not have word region alignments, then VisualBERT simply does not use special aligned position embedding. Instead, each image region receives a default learned position embedding, just like BERT token positions or vision transformer patch position. Okay. But all the regions share the same positioning scheme. All right. So basically, if any extra information about position embedding is not there, it will be just a learnable token. All right. The visual embeddings are then passed to the multi-layer transformer along with the original set of text embeddings, allowing the model to implicitly discover useful elements between the set of inputs and build a new joint representation. Amazing. Now, training VisualBERT. We would like to adopt a similar training procedure as that of BERT, but VisualBERT must learn to accommodate both language and visual input. Therefore, we reach to a resource of paired data, so COCO data set of image caption pairs that contains images, each paired with 5 independent captions. So every image, corresponding to every image, there are 5 independent captions. Our training procedure contains 3 phases. Task agnostic pre-training. Here we train VisualBERT on COCO using 2 visually grounded language models. First, language model objectives. First is MLM, masked language modeling with the image. Some elements of the text are masked, and we will try to predict what those masked tokens from the text are. So, and the masked and must be predicted by vectors corresponding to image regions. Okay, some elements of the input text are masked and must be predicted, but vectors corresponding to image regions are not masked. So this we saw from figure 2. In figure 2, there was no masking in the image region. There was no masking here, but there were masked tokens in the text region. That we understand. Then sentence image prediction. For COCO, where there are multiple captions corresponding to one image, we provide a text segment consisting of 2 captions. One of the caption is describing the image, while the other has 50% chance to be another corresponding caption and 50% chance to be a randomly drawn caption. Do you understand what this means? What this means is, for an image, there are 5 captions available from the dataset. All these 5 captions adequately describe the image. Now, what is given is, for COCO, when there are multiple captions corresponding to the image, we provide a text segment consisting of 2 captions. So we provide text segment in which there are 2 captions. So it will look like this. Let's say I pick caption number 1 for the text segment. One of the caption is describing the image, while the other has 50% chance to be another corresponding caption and 50% chance to be a randomly drawn caption. The model is trained to distinguish these 2 situations. So then the second caption might be picked from either of these four or from the caption of another image. So these five captions are corresponding to image B. These five captions are corresponding to image A. So you will, if you have image A, then for corresponding caption, I will pick caption number 1. Then the next caption might be one of the captions from these four, or it may be one caption from this. In which case, there should be no alignment between, that caption and this caption, or that caption and this image, because that is caption corresponding to a different image. So that is what is done for Coco. I also have one doubt here. My doubt is, are these two captions concatenated or something? That is my doubt. I just want to ask that. Here, is the second caption concatenated with the first caption, or are we constructing another image caption pair using the second caption? This is one of the most confusing parts of the paper. Short answer: VisualBERT concatenates two captions into one long sentence sequence and treats it as a single text input paired with one image. I see. So two captions are concatenated to form one single big caption. If those two captions are coming from the same image, then there is no problem. But if the second caption was with a 50% likelihood pick from another random image, then those two captions are actually not coming from the same image. Okay, because Coco has multiple captions per image. Okay, authors want the model to learn. Sometimes caption 2 describes the same image. Sometimes caption 2 is unrelated. I also want to know, is there a separator token between these two captions? Is there a sep token between these two captions? Yes, there is a separator token between these two captions. Okay, so full structure is CLS token followed by first caption, followed by separator, followed by second caption, followed by separator, and then there will be image tokens also. So let me copy this. After this, there will be image tokens also, right? Show me the full token structure. So there will be, okay, starting with CLS token that we know, then tokens corresponding to caption 1, out of which some tokens will be masked, then separator token, then another tokens corresponding to caption 2, then separator token, then regions from the images. And these captions are also masked, correct? Yes, captions are masked, but only the text tokens are masked. Of course. Yeah, of course. Text token is what is caption, right? Yeah. Okay, I think we understand. So basically, caption 1 and caption 2. Caption 1 is corresponding to the image A. Caption 2 may or may not be corresponding to image A with a 50% probability. Then class token, tokens corresponding to caption A, separator token, tokens corresponding to caption B, separator token, then tokens corresponding to the image regions. And in this, the tokens corresponding to both captions will also have mask. Some tokens will be masked. Okay. Now, so this is the task agnostic pre-training. Then task specific pre-training is before fine-tuning VisualBERT to a downstream task, we find it beneficial to train the model using the data of the task with the masked language modeling with the image objective. This step allows the model to adapt a new target domain. All right. So what is then the difference between what's the difference between these two? I thought both are image caption pair tasks, right? Are we talking about just pre-training once on the new dataset? Here, what is the difference between these two? Is let me just make my is it one in Part A, we have 2 captions, and in part B, we have 1 caption only in the let me ask it in a cleaner way. Basically, what I want to ask is part A is this. Part A is task agnostic pre-training. Part B is task specific pre-training. In task agnostic pre-training, let me just open Whisper Flow so that I can just, just speak instead of typing. So Whisper Flow is a tool that I use for converting speech to text. It's very, very convenient. So I'll just show you how it works. I have installed it. I just need to now press the function key. Here in the task agnostic pre-training, we have 2 captions and we have images. And in task specific pre-training, we have 1 caption and the image. But that image caption pair is from a new dataset. Is this the main difference? So see, it's much easier than typing. So I should have used this before itself, but anyways. High level summary, Coco plus multiple captions uses 2 special, these 2 objectives. 2 captions are concatenated, so this we know. Now in task specific pre-training uses the target dataset, so dataset of the actual downstream task, uses only 1 objective, which is masked language modeling with image. So only 1 caption and 1 caption and the corresponding image are used. Okay, that is good. This is exactly what we thought. So in task agnostic pre-training, we have 1 image and then 2 captions, out of which the caption number 1 will correspond to the image. Caption number 2, with a 50% chance, it may or may not correspond to the image, right? Then masked language modeling is there. And in the task specific pre-training, we just have image caption pair, which is corresponding to that specific data set. And then the last thing is fine tuning. So this step mirrors the BERT fine tuning, where a task specific input, output, and objectives are introduced, and the transformer is trained to maximize performance on the task. Okay, very good. Now we can move to the next section. Section 4, experiment. We evaluate VisualBERT on 4 different types of vision language applications: VQA, Visual Common Sense Reasoning (VCR), Natural Language for Vision Pairing, Visual Reasoning (NLVR2), and then Region to Phrase Grounding, Flickr 30. These datasets we have already discussed about. For all tasks, we use the Karpathy train split of Coco for task agnostic pre-training, which has around 100 images with 5 captions each. I just want to know, what is the Karpathy train split? What is Karpathy train split mentioned here? So it refers to a standardized set of train val test splits for MS Coco image caption dataset created by Andre Karpathy. It has originally these many training, 40K validation, 5K test, but these splits are not designed for captioning benchmark. So Karpathy created a new standardized split, 90K for training, 5K for validation, 5K for testing. All right. Okay, I don't know why this works, but whatever. We'll figure it out when we are reading another paper and for another day. Okay, so the transformer encoder in all models has the same configuration as that of BERT base. So 12 layers, hidden size, which is the embedding dimension of 768, and 12 attention heads. So there are 12 self-attention heads in the multi-head attention. The parameters are initialized from the pre-trained BERT-based parameters released by Devlin et al. Okay, this is a very important thing. So they are not starting from scratch. VisualBERT is not starting training from scratch. It's starting with the pre-trained parameters of the BERT-based model. All right, good to know. For the image representations, each dataset we study has a different standard object detector to generate region proposals and region features. So it's not always necessarily faster RCN, and maybe it's something else. To compare with them, we follow their settings, and as a result, different image features are used for different tasks. For consistency, during task agnostic pre-training on Coco, we use the same image features as in the end tasks. For each dataset, we evaluate 3 variants of the model. So basically, the details of this paragraph we will only get to know when we read further, because this paragraph is describing what is about to be properly explained. So we'll read ahead. VisualBERT, the full model with parameter initialization from BERT that undergoes pre-training on COCO, pre-training on task data, and fine-tuning. So they are calling their model number 1 as VisualBERT, where it does undergo pre-training on BERT data, pre-training on task-specific data, and then fine-tuning. So three levels of, three trainings are there. Pre-training on BERT, it's not done by them. It's already available from the BERT model, but then pre-trained on COCO. And then actually there are 4 levels. So BERT, they use pre-trained BERT model. Then they pre-train it on COCO data, then pre-train on task-specific data, and then fine-tune. So technically there are 4 layers of training happening. VisualBERT without early fusion. VisualBERT where image representations are not combined with the text in the initial transformer layer, but instead at the very end with a new transformer layer. This allows us to test whether the interaction between language and vision throughout the whole transformer stack is important to performance. So basically, let's say there are n transformer layers. According to figure 2, what we saw was the textual representation, text features, and the tokens as well as the image regions are both fed as the token into this particular transformer. But maybe this is the 12th layer of the transformer. How do we know in the previous 11 layers both text and image is fed? In the actual, here I'm not talking about the multi-heads, okay? This 12, please don't get confused with the attention heads in the multi-head. Here I'm talking about number of transformer layers in series. So this VisualBERT without early fusion refers to a model where image is only provided at the end, at the last transformer layer. Till the previous layer, only textual data is provided. So this will allow us to test whether the interaction between language and vision throughout the transformer stack is important or not. Then third is VisualBERT without COCO pre-training. So here the third one is VisualBERT, but where we skip the task agnostic pre-training on COCO. This allows us to validate the importance of this step. Basically, here there were 4, right? One was pre-training on BERT, one was pre-training on COCO, then was pre-training on task data and fine-tuning. In this third one, this pre-training on COCO is removed. So only 3 layers of sort of training is there. So these are the 3 variants of the model that they are discussing. Following Devlin et al., we optimize all models using stochastic gradient descent with Adam. We set up the warm-up step number to be 10% of total training. Batch sizes are chosen to meet hardware constraints. So then they are just discussing about what kind of hardware they use. Pre-training on COCO generally takes less than a day on 4 these GPU cards, Tesla V100, GTX 1. So basically these are some details about the training if you were implementing it. Since I'm not implementing it right now, I'm not going to check the exact details of this implementation. Now the paper is discussing the task, visual question answering, visual common sense reasoning. There were 4 tasks, right? So if you look at it, 4.1 and 4.2 is visual common sense reasoning. 4.3 is NLVR, natural language visual reasoning. 4.4 is Flickr dataset. And only then we move to the 5th section. So now we are going into the details of these 4 tasks. Let's start with VQA. Given an image and a question, the task is to correctly answer the question. We use the VQA 2.0 consisting of over 1 million questions about images from COCO. We trained the model to predict 3,129 most frequent answers and use image features from ResNext based faster RCNN pre-trained on Visual Genome. More details are there in appendix. So ResNext paper is super famous. Almost 15,800 citations. So this is the one. I also hope to, at some point, I also hope to do a review of this paper. But right now, I just want to show you this. I have no intention to, properly walk through the paper. Anyways, we report the results in table 1, including baselines using the same visual features and number of bounding region proposals as our method. Okay, one question that I have here is, we can ask that to ChatGPT. We have 100,000 images or something and 1 million questions. And for all those 1 million questions, there are a lot of common answers. So let me ask ChatGPT to make sure whether that is indeed the case or not. I'm just trying to understand this data set. in this VQA task, you have, let's say 100,000 or 80,000, how many ever number of images there are in COCO, and there are total 1 million questions, and total number of frequent answers are around 3,000-ish. Is that correct? How many total unique answers are there corresponding to these questions, corresponding to these 1 million questions? Okay, so VQA has around 120K images, counting train and validation. Train is 80K, but if it is a Karpathy split, it's more than that. Then each image has 3 questions on average, which means around 1 million questions. Okay. Each question has 10 human answers. So there are around 11 million answers. There are around 260,000 unique answers, but top 300 and top 3,000 answers. This is the official 3K answer set. Okay. So these are the most frequent answers to all the 1 million questions. But for some questions, the answer may be completely different. Okay. So that's basically the data set. We report the results in table 1, including baselines using the same visual features and number of bounding region proposals as our method. So baselines meaning some other baseline models which use similar number of region proposals as this method, then our models and other incomparable models in the third section. So I guess these models are incomparable. I don't know why they are not comparable. Because yeah, I guess they use external question answer pairs from visual genome and multiple detectors and ensembles in their model. Okay. That's the reason why it's not incomparable. It's incomparable. In comparable settings, our method is significantly simpler and outperforms existing work. So these two are comparable in terms of size. I don't think any of this is state of the art. So this model is not claiming to be state of the art. And which is the reason why the paper is not as famous, because you have to achieve state of the art for you to be super famous. But this model is comparable compared to similar models of similar size. The performance is much better, right? So on the test dataset, it has 70% performance. If you use VisualBERT, so here VisualBERT with BERT pre-training, COCO pre-training, task specific pre-training, and fine-tuning. That's the last one, which has the best accuracy, 70.80. The previous models, Pythia, I don't know what this model is. Maybe we can ask ChatGPT, what is this Pythia model? What is this Pythia model? It's a strong VQA model developed by Facebook AI Research around 2018-19. It was one of the state-of-the-art baselines on VQA 2.0. Okay, already. Okay, this was one of the state-of-the-arts at that point of time. So I guess this was pretty good in that sense. Okay. And then these models, I guess, are trained on other datasets also from visual genome, not just from the VQA COCO dataset, which is why you can't compare VisualBERT and these models. But although, I mean, of course, the authors will say that because their performance is, of course, better. But they're also saying the reason why it's better is because you are using external question answer pairs plus ensemble models, etc. Okay. Now coming to visual reasoning. Visual common sense reasoning. VCR consists of 290K questions derived from 110K movie scenes, where the questions focus on visual common sense. The task is decomposed into 2 multi-choice subtasks wherein we train individual models. So one is question answer model and an answer justification model. Image features are obtained from ResNet 50. So what about faster RCNN? I just want to know in VisualBERT paper, what model is used for extracting the features from the image? Is it faster RCNN or is it ResNet or is it something else? Because to draw bounding box, you need something like faster RCNN, some sort of object detection model, right? Image features come from faster RCNN, not ResNet. Okay, I see. Fine. But here they mention ResNet. Image features are obtained from ResNet and gold detection bounding boxes and segmentations provided in dataset are used. All right. The dataset also provides alignment between words and bounding regions that are referred to in the text. So what this means is if the bounding region is that of a necktie of somebody, there will be some caption, image caption in which the word necktie is there. So that word and this bounding box region will have some alignment. So dataset also provides those alignments, which we utilize by using the same position embedding for matched words and region. So this is very, very, very important. See, in position embedding, we discussed earlier that if it's just a image caption dataset pair, then there is no position embedding concept for the image regions, because what do you mean by position embedding for an image region? However, if a certain image region is strongly correlated with a certain word in the text input, and if that correlation or that alignment is part of the training data, then you can use same position embedding for that particular token or that particular word and that particular region. So that is what is mentioned here. More details we will see in the appendix. Results on VCR are present in table 2. We compare our methods against the model released with the dataset which builds on BERT R2C and lists the top performing single model on the leaderboard. Our ablated VisualBERT without COCO pre-training enjoys the same resource as R2C, and despite being significantly simpler, it outperforms it by a large margin. The full model further improves the results. Despite substantial domain difference between COCO and VCR, with VCR covering scenes from movies, pre-training on COCO still helps significantly. Okay, because the VCR dataset is not COCO, it's from movies. Let's do one thing. I'll just put a screenshot to ChatGPT. I just want to understand the dataset a little bit. So can you explain me the dataset? So how do you construct the reasoning from visual? I just want to know how the ground truth data looks like. Okay, so dataset, it's from movie scenes, not object detection, where the goal is not object detection and it's not captioning, but it's Y type reasoning. So you have an image frame, which is from movie, then you will have a question associated with the frame, then you will have 4 answer options and 4 explanations corresponding to each answer. So which means there are total 16 explanations. Is that correct? Object detection boxes within indices, then alignments between words and bounding box IDs. Okay, so this is how it looks like. Objects each, so you will have an image which is a frame from a movie. Then each detected region has an index. So if there is a man, if there is a bounding box corresponding to a man, corresponding to a woman, corresponding to a chair, then those regions will have indices 1, 2, 3, 4. Then the question is something like this. Oh, I see. Why is 2 looking at 1? Okay, so here, this is how text and image alignment is coming. Why is 2 looking at 1 means we know that 2 is woman and 1 is man. So the question is, why is woman looking at man? Here 2 refers to bounding box number 2, which is woman. 1 refers to bounding box number 1, which is man. Okay, now I understand it better. Then the answer choices are, these are the 4 answers, because 1 is talking to her, because 2 is upset about something unrelated, because 1 is, okay, so these are now 4 answers. Now let's say correct answer is answer number A. Now there are now 4 reasons corresponding to why this answer is correct. So rationale number 1 is she seemed engaged in the conversation. He is pointing something out to her. They are arguing about something. She is making fun of him. Then the correct rationale is A2. So basically for the given image is not shown here, but for that image, there are a bunch of detected regions inside. The image is a frame from a movie. And inside the regions, there is man, woman, chair, window, etc. Question is, why is woman looking at the man? These are possible answers. Corresponding to each possible answers, there are 4 possible explanations, but correct answer is answer number what? A, right? This is the correct answer. And among the 4 possible explanations for that answer, this is the correct explanation. Okay. So just to understand, so do we have 4 answer options and corresponding to each option 4 rationales? So are there total 16 rationales per question? Is that correct? Okay, I just want to understand if this is actually correct or not. No, that is not how VCR is structured. This is a common misunderstanding, and okay. So there are 4 answer choices and 4 rational choices, but the rationals are not tied to, I see. So it's not like every answer has 4 rational. There are 4 answers and 4 rationals. You need to pick the correct answer and the correct rational. Oh, okay, I see. So there are, okay, that makes it clear. Good that we asked. Okay. So that is the visual VCR dataset. Let's just look at the result. So this is VisualBERT without COCO pre-training, and this is VisualBERT with COCO pre-training. And if you look at the QA task, question answering task, oh, what are these 3 tasks? I just want to know. What are these 3 tasks mentioned in the table here in 3 columns? So my understanding is this is question answering, this is question answering to reason, question to answer reasoning. Okay, let's see what is the definition. First is question to answer. Okay, for sure, this we understand. There were 4 options. We need to pick which is the correct option. Then question plus correct answer, you try to map it to rational. So this is the reasoning justification stage. So your input will be image, question, correct answer, and then you just need to pick the correct rationale. Okay, I see. So you're not predicting answer and rationale at the same time. Answer is already available as part of the input. You are just trying to pick the correct rationale. Third task is you want to pick the answer as well as rationale. So input will not contain the correct answer. Input will contain image, question, and those correlation between different objects in the image with the object name. Then in the output, you should pick the correct answer and pick the correct rationale. Okay, which is the hardest task, I guess. So the accuracy probably will be lowest there. So here, question to answer, the VisualBERT model has 71% accuracy. If you know the question and if you know the answer, and if you have the image, you have a lot of inputs, you just need to pick the rationale. On that, the accuracy is highest. But if you only have the question and image, from that, getting the correct answer and getting the correct rationale is most difficult. The accuracy is only 52. So that makes sense. And I guess here they are trying to compare with comparable models, and the performance of VisualBERT is better. So this is VisualBERT with pre-training on BERT, pre-training on COCO, pre-training on the specific data set which we are looking at here, and then later, if needed, fine-tuning. Okay, so that is it. Now NLVR. NLVR dataset is for joint reasoning about natural language and images with a focus on semantic diversity, compositionality, and visual reasoning. The task is to determine whether a natural language caption is true about a pair of images. So you'll have pair of images and you will say, okay, in image number 1, there are 3 dogs, and image number 2, there is 1 dog, something like that. The dataset consists of over 100K samples of English sentences paired with web images. We modify the segment embedding mechanism in VisualBERT and assign features from different images with different segment embeddings. This is what we had discussed. There are two sentences paired with web image, right? Basically, 2 captions are paired with, or rather, 1 caption is paired with 2 images. So earlier we had a thing where 2 captions were paired with 1 image. Here it is 1 caption paired with 2 images, which means there are 3 segments. Segment number 1 is for the text. Segment number 2 is for the image number 1. Segment number 3 is for the image number 2. Let's see if that is indeed the case or not. Here, after tokenization, how does it look like? You have CLS token followed by text tokens with mask, then separator token, then the tokens corresponding to image number 1, then another separator token, then tokens corresponding to image number 2. Is that how the embedding looks like? Thinking in exact right direction, but let me give you precise. Okay. Caption image 1. So fine. Yes, input looks like CLS followed by caption, then separator, then regions in the image followed by separator, regions in image 2 followed by separator. This we know. It needs 3 segment embeddings, of course. 1 for the text caption, 2nd for image number 1, 3rd for image number 2. That also is fine. I just want to know if the text has masking. Is there any masking in the text in this case? I am I think there should be masking, but I just want to be clear. And while that response is getting generated, let's read ahead. We use an off-the-shelf detector from Detectron to provide image features and use 144 proposals per image. So basically what I understand is to get image proposal, region proposals, there are different region proposal models. It's not always faster RCNN. So let me just ask that. Okay, so firstly, is there masking? There is no masking during fine tuning. VisualBERT does not apply masked language. Oh, I see, I see. So masked language modeling is not applied in the fine tuning stage. It is only applied in the pre-training stage. Okay, that is good to know. It's just binary classification of true or false. Okay, so for NLVR task, whether the caption describes both images simultaneously or not. Okay, I see. Masking would hurt the performance because model must see the full caption to make a judgment. Okay, for sure. Makes complete sense. Now my question is, I want to know, here it says they use Detectron to create the region proposals. So are we not using faster RCNN in this case? What all different region proposal models are being used for these task specific experiments in VisualBERT paper? I think in BERT pre-training, they use faster RCNN. Okay, VisualBERT uses different feature extractors depending on dataset. For Coco, they use faster RCNN. For visual common sense reasoning, they use ResNet 50. NLVR2, they use Detectron 2. Flickr 30 and visual question answering, for that, both of them, they use faster. Okay, so they use these three different types, faster RCNN, ResNet 50 and Detectron 2. Faster. Okay, this is also a variant of faster RCNN. Okay, for sure. Okay, instantiated faster RCNN inside Detectron, and for VCR, they use ResNet 50 based detector. Okay. It's not like they are 100% always using faster RCNN. So now this is the comparable model they are comparing against, and VisualBERT, of course, outperforms it in all the data sets. But I don't think this is the state of the art. So by no means this paper is claiming state of the art. The only claim that this paper makes is for comparable number of parameters, there is no other better performing model. Okay. Now Flickr 30K entities. Flickr 30K entities dataset tests the ability of systems to ground phrases in captions to bounding regions in the image. So in the caption, there are a bunch of phrases, and that phrases are not fully connected with the whole image. It's connected to one region in the image. The task is, given the spans from a sentence, selecting the bounding regions they correspond to. The dataset consists of 30K images and nearly 250K annotations. We adapt the setting of ban, where image features from a faster RCNN pre-trained on visual genome are used. For task-specific fine-tuning, we introduce an additional self-attention block and use, okay, I just want to know what the dataset looks like. That's the main thing here. How does the Flickr 30 dataset look like? Basically, what is the input that goes into VisualBERT? My audio to text converter converted it into VisualBERT instead of VisualBERT. Anyways, doesn't matter. So Flickr 30 has dataset with phrase grounding annotation. So you have an image, you have a caption, which is a sentence, then phrases in the caption referring to objects, then bounding boxes for each phrase. Okay, this is an example. A young boy is playing with the frisbee near some trees. Then bounding boxes are box number 12, and then that is connected with the phrase boy. So maybe there is like a JSON file or some table which connects the phrase boy with the bounding box number or bounding box ID. So each phrase has one or more bounding boxes grounding it. Okay, very good. Because trees means maybe there are multiple bounding boxes corresponding to trees. So the phrase trees from the caption might be corresponding to multiple bounding boxes. Okay, so this is the data set. So given a phrase, so if the task is basically given frisbee, find the boxes in the image that correspond to it. So basically VisualBERT must align text spans to image. So what input goes into the VisualBERT? The text input, the caption, tokenize. So tokenized caption that looks like this. To ground a specific phrase, VisualBERT focuses on the tokens of that phrase. So we take the attention from the last subword of the phrase. Okay, so if the phrase is frisbee, last subword is what? B, something like this. Is that the last subword? Yeah, only the embedding of B is used for attention-based grounding. Then that should predict box number X, box number 12. I just want to see the output. Input sequence. So input sequence will look like a young boy is playing with frisbee near trees, separator token, followed by the image regions. Then segment A is the caption words. Segment B is all the regions from the image. Then selects the region with the highest attention as the predicted grounding box. I see. So let's say this frisbee is tokenized as fris and B. Then B is the last sub part of this token. And then what is done is, if that token is the query, if that is converted into query, which among these regions does it attend to mostly? The attention score between the query corresponding to B and key corresponding to these visual boxes. Which one is the highest? That is what the prediction is. Okay. That makes sense. Okay, in one line, Flickr30 data entities is an image caption dataset where each noun phrase is in the caption is linked to bounding boxes, and VisualBERT must use cross-model attention to ground the phrase to correct region. Okay. JSON example. Okay, all this, I don't think we need to see the JSON file. Let us read the sentence once again. Now we'll understand it better. The task is given spans from a sentence, selecting the bounding regions they correspond to. The dataset consists of these many. Okay, for task-specific fine-tuning, we introduce an additional self-attention block use the average attention weights from each head to predict the alignment between boxes and phrases. For a phrase to be grounded, we take whichever box receives the most attention from the last subword of the phrase as the model prediction. So if frisbee is tokenized into fris and B, B is the last subword corresponding to the phrase frisbee. Now the B, if you convert it into a query, we need to know which key does this query attend to the most, or to which token does the token B attend to the most. That token will be, and that too from the visual tokens, not from the textual text tokens. From the visual tokens, whichever token gets the most attention from B, that is the final predicted bounding box. Okay. Results are listed in table 4. VisualBERT outperforms the current state-of-the-art model ban. Okay, this is amazing. In this setting, we do not observe a significant difference between the ablation model without early fusion and our full model, arguing that perhaps shallower architecture is sufficient for this task. So this is good to know, because do you remember what is this without early fusion model? Without early fusion meaning image data you are only feeding in the last transformer layer. Previous transformer layers are only getting the textual data, which means many of those layers you could probably remove. Perhaps a shallower architecture is sufficient for this task. That's what this means. Table 4, let's see the results. So this is table 4, and this ban model is the state of the art. And here you can see there is not much difference between the without early fusion case and with early fusion. 70.33, 70.40, 84.53, 84.49, 86.39, 86.31. So very much similar. But Cocoa fine-tuning seems to be a big deal. If you don't have Cocoa fine-tuning, Cocoa pre-training, the performance is significantly lower. All right. So this is very good. Now let's move on to analysis. In this section, we conduct extensive analysis on what parts of our approach are important to VisualBERT's strong performance, sort of like a ablation study. Then we use Flickr30 as a diagnostic dataset to understand whether VisualBERT's pre-training phase actually allows the model to learn implicit alignments between bounding regions and text phrases. We show that many attention heads within VisualBERT accurately track grounding information, and that some are even sensitive to syntax, attending from verbs to the bounding box regions corresponding to their arguments within a sentence. I want to see this result actually. Finally, we show qualitative examples of how VisualBERT resolves ambiguous groundings through multiple layers of transformers. So these qualitative examples are probably, they have some images shown in the, I think, 10th page or something. I think this one. So maybe they are referring to this. I'll come to this. Maybe these are the qualitative examples. Anyways, let's go back and come to this section separately. Okay, now we come to the ablation study. We conduct our ablation study on NLVR2 dataset and include 2 ablation models in our, I think this is called section 4, right? And 4 additional, or what is this? Section 4, or what is this symbol? I'm not 100% sure, so I'm going to ask ChatGPT. What does this weird symbol followed by 4 mean? Not a mathematical notation. Okay, section symbol. All right. Okay. So it means section 4, 4 additional variants of VisualBERT for comparison. For ease of computation, all these models are trained with only 36 features per image, including the full model. Our analysis table 5 aims to investigate the contribution of the following components. So one component is task agnostic pre-training. Another component is early fusion, whether the image should be available from the first transformer block itself or not. Third is BERT initialization. I mean, we know these tasks already. Fourth is sentence image prediction objective. Okay. This is the objective specific fine tuning, I think. Okay. So we'll see what is the importance of these 4 things. So this table 5, let's see. VisualBERT is the BERT model with everything done. It has highest accuracy, performance on NLVR2 dataset. VisualBERT without grounded pre-training, and VisualBERT without COCO pre-training. Without grounded pre-training means, I guess, let's start from this. Without BERT initialization means you have 64.7. So this has 3 things. It has COCO pre-training, it has task-specific training, but it does not have BERT. This means early fusion, the image is allowed to appear only in the last transformer layer. That significantly impacts the performance. VisualBERT without Objective 2. Objective 2 is, I guess, classification, right? Objective 1 was the mask prediction, if I remember correctly. Let's check the figure 2 once more. Yeah, this is figure 2. Yeah, objective 1 was mask prediction. Objective 2 was to predict whether the caption and image are from the same pair. That was objective 2. So if objective 2 is not there, I think it should impact the accuracy. Let's see what it does. Yeah, objective 2, if it is removed, accuracy is impacted, but not as much as I would have expected. Results confirm that task agnostic pre-training and early fusion are essential. C1 and C2 are essential. Okay. Then figure 3, we did not look at this yet. Entity grounding accuracy of the attention heads of VisualBERT. The rule-based baseline is drawn as gray line. We find that certain heads achieve high accuracy while accuracy peaks at higher layers. So the grounding between the bounding rectangle and the phrase in the caption, the alignment between those two are higher in the later layers than in the early layers is what this is showing. But what is this top curve? Is this the best accuracy? Let me ask ChatGPT, what is the line shown at the top? In this figure from the VisualBERT paper, what is the line that is shown at the top? The line that connects the dots. My pronunciation is so bad that it's taking BERT as bird, but whatever. 12 layers, each layer has 12 attention head. They compute grounding accuracy for each 12 heads and plot these accuracies as individual scattered points. Okay, then maximum accuracy among those 12 heads. The plot that as a larger dot for that layer. Okay, they are just showing the best head. So these lines basically connect the best performing head in each layer, because in each layer you have 12 attention heads. So it's multi-head attention. So in every layer you have parallel 12 heads. Like that, you have 12 layers. And here they are taking the head which performs the best. And what they are showing is we find that certain heads achieve high accuracy while the accuracy peaks at higher layers. So these are the best performing heads. We don't know the head number. We don't know whether it is head number 1, number 2 or not. It's just showing accuracy. So some heads achieve high accuracy, and in general, later layers achieve high accuracy. So this is how you go from layer 1 to layer 12. And within each layer, you have 12 attention heads. You will most likely have 12 dots here if you count. So some heads in each layer has higher accuracy. All right. So that is what this figure 3 is showing. Okay, so C1 is task agnostic pre-training. We investigate the contribution of task agnostic pre-training by entirely skipping such pre-training. VisualBERT without COCO pre-training. So the effect of this pre-training can be investigated only if that pre-training is avoided altogether. And also by pre-training with only text but no images from COCO. Okay, that is interesting. Both variants underperform, showing that pre-training on paired vision and language is important. Of course, we know that. Early fusion, we include VisualBERT without early fusion to verify the importance of allowing early interaction between image and text, confirming again that multiple interaction between vision and language are important. Just introducing vision in the 12th layer is not enough. Then BERT initialization. All models are so far initialized with parameters from pre-trained BERT. To understand the contributions of BERT initialization, we introduce a variant with randomly initialized parameter. Then the model is trained, the full model is trained. While it does seem weights from the language only pre-trained BERT are important, the performance does not degrade as much as we expect. So C3, this is C3. And look at this, C3's performance is not as bad. So maybe BERT initialization is not needed. While it does seem weights from language only model pre-trained BERT are important, the performance does not degrade as much as we expect, arguing that model is likely learning many of the same useful aspects about grounded from COCO pre-training. So BERT's pre-training is probably not needed. Even in the absence of that, from the COCO dataset pre-training, the model is learning most of the things. Then C4 is sentence image prediction objective. We introduce a model without the sentence image prediction objective during the task agnostic pre-training. Results suggest that objective has positive but less significant impact compared to other components. Okay. Overall results confirm that most important choices are task agnostic pre-training. So we have to pre-train with some sort of like, sentence pair, sentence followed by image, sentence image dataset pair from COCO, and early fusion is also needed. So COCO pre-training is needed and early fusion is needed. Those are the two most important things that this model requires based on the ablation study. And you must have realized by now that we are almost done with the paper review. This is the 8th page and next page is the last page basically. Remaining pages are, there is not much in the remaining pages. So let's look at 5.2, dissecting attention weights. So entity grounding. In this section, we investigate which bounding regions from the image are attended to by words before VisualBERT is fine-tuned on any task. So entity grounding, first we attempt to find attention heads within VisualBERT that could perform entity grounding, that is attending to corresponding bounding regions. This is what we saw in figure number 1. From entities in the sentence. Specifically, we use the ground truth alignments from the evaluation set of Flickr 30 for each entity in the sentence, and for each attention head in VisualBERT, we look at the bounding region which receives the most attention weight. Basically, let's say the label corresponding to a bounding box is man, and that man is also, let's say, present in the sentence. Then ideally, that particular token in the sentence should have the highest attention to this particular bounding box, not to some other bounding box that encloses a building or something like that. Because a word is likely to attend to not only the image regions, but also to words in the text. For this evaluation, we mask out the head's attention to words and keep only attention to image regions. Oh, interesting. I did not know this. Did you understand what they're saying? What they're saying is, see, in self-attention, all tokens attend to all tokens. In the tokens, you have words and images, right? But here you want to visualize the attention paid by text tokens to image tokens. You don't care about attention paid by text tokens to itself. So what is done is you mask the attention from text to text. You just construct attention from text to image. Then we compute the how often the attention of a particular head agrees with the annotations in Flickr 30. Okay, excellent. We report this accuracy for all 144 heads organized by layer in figure 3. Yeah, figure 3 we already saw. In figure 3, we saw that some heads are really good, some heads are not good, and in general, later layers are performing better. That's what we saw from figure 3. All right. We also consider a baseline that always chooses the region with the highest detection confidence. We find that VisualBERT achieves remarkably high accuracy, though it is not exposed to any direct supervision for entity grounding. The grounding accuracy also seems to improve in higher layers, showing the model is less certain when synthesizing the two output in lower layers, but then becomes increasingly aware of how they should align. Okay, we show some examples of this behavior in section 5.3. We'll see that. Syntactic grounding. Given that many have observed that the attention heads of BERT can discover syntactic relationship, we also analyze how grounding information is passed through syntactic relationship that VisualBERT may have discovered. In particular, given two words that are connected with a dependency region W1 to W2, we would like to know how often the attention heads at W2 attend to the regions corresponding to W1 and vice versa. For example, okay, so far this I cannot understand. It's all a generalized statement. I just want a specific example. So now we are at the specific example. For example, in figure 1, we would like to know if there is an attention head that at the word walking is systematically attending to the region corresponding to the man, because man and walking are related through the n sub j relation. Basically, man is the person who is walking. So does the word walking attend to the region in the image which encloses the man in figure 1? So there was a bounding box that was enclosing the man in figure 1, right? And the question is, the word walking in the description of the image, in the caption of the image, is that attending to the region corresponding to the man or not? So that is what they were trying to do. To evaluate such syntactic sensitivity in VisualBERT, we first parse all sentences in Flickr 30 using NLP's dependency parser. Then for each attention head in VisualBERT, given that two words have a particular dependency relationship and one of them has a ground truth grounding in Flickr 30, we compute how accurately the head attention weights predict the ground truth. Examination of all dependency, we highlight. I think this is like a very dense sentence, not very nicely written unless we see a good figure. So we would like to see now which one, figure 4, correct? I want to see what is figure 4. Then maybe we can understand this paragraph better. Okay, so this is figure 4. So P object n sub j dobj a mode. I don't understand what are these y-axis dependency relationship. Let me ask ChatGPT, what are the y-axis labels here? What are the y-axis labels here? What are the y-axis labels here? Let's read the caption. Meanwhile, I hope you understand the figure itself, even though you don't understand the y-axis label. These are different attention heads in the multi-head attention for each layer. So these are the attention heads in first layer. This is in second layer, third layer, and so on. For different y-axis labels. Now we'll see what are these y-axis labels for predicting 4 specific dependency relationships. What are these dependency relationships? P ob means prepositional object. A mod means adjectival modifier. I just want to see examples. I don't want to hear definition. Okay, P object means example on the table. Table equal to P object. Okay. Then adjective modifying a noun. Red ball. So red is the adjective. N sub, boy throws. Boy is the noun. Okay. Okay, noun subject. D object means direct object, throws the ball. The ball is the object that is being thrown. Okay, I see. All right. So now the question is accuracy of attention heads of VisualBERT for predicting 4 specific dependency relationships across modality. The gray line shows baseline that always chooses the region with highest detection confidence. We observe that VisualBERT is capable of detecting these dependency without direct supervision. So am I supposed to now understand that what are these big dots? I don't understand what are these big in the figure. What are the big green dots? VisualBERT has 12 attention heads. Each attention head gets a grounding / dependency accuracy score. All heads scores are shown in small dots. Okay. The highest accuracy among the 12 heads in that layer is big green dot. But then how come you have multiple within the same head you have multiple big green dots? Let me ask that. Then how come in figure 4 within the same layer you have multiple big green dots? Okay, yeah, I want to know about figure 4, not figure 3. Large dots represent mean accuracy of all the 12 heads in that layer, not the best head. Therefore, big dots are layer-wise average of 12 heads. Layer-wise average of 12 heads. Wait, but I don't think I understand what are these big green dots. It's not making sense at all. Figure 3 was okay because in figure 3 I thought the dot were showing the where is figure 3? Okay, here also there are multiple green dots actually. Yeah, I think I did not understand why there are multiple green dots. Multiple big green dots within the same layer. I just want to understand what is that. So these are figure 4 and figure 3 respectively. I think I understand the x-axis. The x-axis is different transformer layers. And on y-axis, corresponding to each layer, I think there are 12 multiple attention heads. So there are 12 heads per layer. So those are the 12, I guess, dots. But I can see that within each transformer layer, there are sometimes more than one dot that is shown in a bigger size. Why is that? What does that mean? Imagine how would I understand this if ChatGPT was not there. I would have had to spend a lot more time. So this is one thing I like so much about LLMs. Like it helps you learn things. Although it has hallucination, its writing is really bad. I really learning is much better. Okay, so there are 12 attention heads per layer. We know that. For each layer, authors find the single highest accuracy head. Okay, that head gets a big dot. Just one per layer. No, it's not one per layer. How come? I can see more than one per layer. There are more than one per layer. So what are they saying? I don't understand. The line connects these big dots. Figure 4, here each subplot has its own big dot. So across you see multiple big dots in the Y because in figure 4 big dot equal to layer average accuracy. Okay, sure. Model evaluates all 12 heads per layer, computes 12 accuracy values, 1 per head. Okay. These appear as small dots and then computes mean accuracy across 12 heads. I don't think what ChatGPT is saying is making sense at all. So here, guys, this is my question. I'll be so grateful if you can answer. I don't understand what these big green dots mean. If any of you can clarify this in the comment, I'll be happy. in figure 4 also, I don't understand what the big green dots mean. Let me just read ahead. Maybe they are explaining it somewhere. Finally, we showcase several interesting examples of how VisualBERT changes its attention over the layers when processing images and text. In figure 1 and figure 5, okay, in figure 1 and 5, they are showing that. To generate these examples, for each ground truth box, we show a predicted bounding region closest to it and manually group the bounding regions into different categories. We also include regions that the model is actively attending to. All of this we can understand if we simply look at figure 5. Figure 5 is this, I guess, right? Attention weights of some selected heads in VisualBERT on 6 examples. First column is 3 random examples where alignments match flicker 30 annotations, while second column is 3 random examples where alignments do not match. Okay, so this and this are where alignments match. This and this are where alignments do not match. So this tennis example we already looked at. Oh no, actually we did not look at. We looked at the person who was walking. A person hits a ball with a tennis racket, right? So now this red color box is person, which means this person thing should be highest correlated with red. This. Is that the case? Yes, towards the last layer. Indeed, that's the case. This row is person, this column is person. Then ball is blue color box. So blue color box should be ball. This is ball, this row, and blue is this. So in all the layers, ball word is correlated with the ball box, bounding box around the ball. So this is where alignment is there. Now let's look at an example where there is no alignment. Let us pick this example. Here, 2 musicians are playing a tune together at a construction site. Now, 2 musicians should be a red box. So is there good alignment? Musicians is the word. Ideally, it should be correlated with the first column. It is correlated in layer 4, in layer 5, in layer 6. But in layer 11, there is poor correlation. Layer 10 correlation is not good. In layer 3, the correlation is not good. Are playing a tune together. So playing tune together at a construction site. So playing, hopefully that word playing should be correlated with maybe yellow, right? Because hands, you play using your hands or something. So the word playing should be correlated with column yellow. Column yellow is third column. So yes, there is high correlation. There is high correlation. Here also there is high correlation. Here is also there is high correlation. I just want to see a case where there is no correlation. Blue. Okay, blue is also musicians. So musicians is correlated with. There is 0 correlation with the blue. Okay, so blue rectangle is bounding both musicians, and that is the label of the musicians. And this word musicians has 0 correlation with the column number 2. No correlation, less correlation, no correlation, no correlation, no correlation, no correlation. In none of the layers there is a correlation. So there is misalignment. Now let's look at this one. There is supposed to be misalignment. A man wearing Revolutionary period clothes is ringing a bell. Okay, now bell is which one? Bell is this light blue or dark blue? Both are bell. So light blue and dark blue are bell. So the last one should have correlation with second column and last column. There is actually poor correlation. Second and last, poor correlation. Second and last, extremely bad correlation. Second and last, extremely bad correlation. Bad correlation, bad correlation. So yes, this is where a misalignment is there. Wearing a Revolutionary period clothes. A man, maybe man is connected with, okay, red rectangle is man. Red rectangle is first column. So bad correlation, good correlation in this layer, layer number 5. Bad correlation, okay correlation. So you can see that the bell was a very good example of misalignment. So this is what figure 5 is showing, examples of misalignment. And that's pretty much it. That's the end of the paper. We can now read the conclusion section, conclusion and future work. In this paper, we presented VisualBERT, a pre-trained model for joint vision and language representation. Despite VisualBERT is simple, It achieves strong performance on 4 evaluation tasks. Further analysis suggests that the model uses the attention mechanism to capture information in an interpretable way. For future work, we are curious about whether we could extend VisualBERT to image-only tasks such as scene graph parsing or situation grouping, situation recognition. Retraining VisualBERT on larger caption datasets such as visual genome and conceptual caption is also a valid direction. All right, all of this is good. Now, is there any other section, references, implementation and training detail? I think this part is fine. This is just the details of implementation, which you can read if you plan to implement this. But other than that, conceptually, we have covered pretty much everything. So that is the end of the VisualBERT paper. It took us some time to go through this, and I'm pretty sure by this point you are very tired because this has been a bit long video as usual. I mean, none of the research paper dissection videos are short. But we have covered so many in this series now. We have gone through vision transformer, BERT. We had gone through data efficient image transformer, SWIN transformer, and now we are also at VisualBERT. And today's lecture actually gave me a few ideas. I think we should go through this video BERT paper. It looks very interesting. We should definitely do a breakdown of VilBERT. We should definitely do a breakdown of this OpenAI, this paper, GPT paper, and of course, attention is all you need. I'm reserving that to a bit later because I mean it's very famous paper and many people have already read it. Although it's a dense paper, it's very famous. So I thought I'll cover all the other bases before coming to attention is all you need. So all right, that is a good place to end this lecture. Thank you so much for listening. I'll see you again in another lecture. Most likely one of these which I have mentioned. I have not exactly decided which one to dissect next. But I hope you enjoyed this lecture and I hope you learned a lot. We'll see again each other in the next one. Take care until then.